Welcome back to the Q&A session of mobile communications. Today we start with a new chapter, chapter 5, wireless local area networks. So I told you a bit about these different technologies, and today we mainly look at wireless LANs. This is already complex enough. And then in the following sessions we will handle Bluetooth. And in this context I explained different topologies of wireless LANs, so infrastructure networks, ad hoc networks, and these are the topologies I guess you've been already in contact with. Infrastructure, that's our normal structure you have at home, and maybe also ad hoc. So if you have some kind of wireless printing over the air, and then there's also the possibility of a mesh network. So these were the basic settings. And I also said that this standard, which is already more than 3,500 pages, mainly covers the lower layers. So here the MAC and physical layers, so the radio transmission, etc. And these are the typical layers IEEE is dealing with. Okay, so some more general questions, and please do have a look at the web pages of IEEE. You saw already at the slide number 2 that there are so many standards and substandards, and the substandards will then go into the main standard after a while. Some standards are simply dead, some of the working groups are hibernating. So if you're interested in this, check the web pages, and then you will see what's going on there. Okay, some first questions. I mean, if you look at the wireless LANs and at the, well, for example, infrastructure, this topology. So what about mobility? I mean, you are mobile, but so what is the problem there? Think of wireless LANs are usually on layer 2. So what do you need additionally if you really want to roam? And how can you support the roaming? There are many different answers possible. Think of you walking across a city, a campus, or at home. What do you need for roaming? Roaming is the handover term in wireless LANs. Yeah, you need a distribution system, some kind of distribution system. That's one thing you need. So IEEE does not specify how you do this. So if you look at the campus, for example, there are what is quite common, proprietary systems that a company offers you access points, which are basically smart antennas, and then says, okay, and we have a distribution system somewhere inside the network, and we will handle this handover between different access points. So that's one thing you need. And you need protocol between the access points. Exactly. So, and the point is that the wireless LAN standard does not cover the distribution system. This standard does not cover any, as you write, the authority to authorize the access to other people's network. Exactly, that's not included in this standard. The standard covers the medium access and the physical layer. You need switching on layer 2. So this is all true. And additionally, you may even need layer 3 routing. Just imagine you want to have a handover between your wireless LAN and the public wireless LAN. Well, this is not solved by the wireless LAN standard. Then you need additional routing, and as you write, you need some authorization. So why should another wireless LAN let you inside the network? Maybe you know this, that there are many hotspots you can use. If you have a contract with a certain operator, suddenly you can use also private wireless LANs. So this means you have many hotspots. Or we have the ad-hoc system, but there you have all the authorization at your home university. So you have an account at your home university, and then no matter where you are on this planet, as soon as you see Eduroam as network, then the system knows, okay, authorization is done by your home, whatever, university, for example. So this is all not specified by the standard. So there are some ways for authentication, for this exchange of authentication messages in the standard, but not the infrastructure behind how you really do this, especially if you have wireless LANs operated by different people. So it's not like the big mobile phone networks where you have single operators handling this and then agreements between the operators. So roaming, additionally, typically you use the same SSID. So this SSID, the service ad identifier, that's usually what you see as the name of the network. So then if you have the same name and everything else is set up, then you can switch between access points. So that's also something you can do at home, but there might be some problems. So depending on if you have a switch and then you switch over from one access point to the other, sometimes you have an interruption in the connection, etc., etc. But again, this is all not handled by the standard. Okay, so it's not like this seamless handover between, let's say, one operator and other operator in mobile phone networks. Not even that seamless, well, as you know it from mobile phone networks, from one base station to another base station. So there's a lot more needed. And this is why, for example, on our campus, we have a specialized infrastructure for this. So we have this kind of specialized distribution center where all the antennas are connected to, and then you can perform this kind of more or less seamless handover from one access point to another one. Okay, and at this high level, if you compare our wide area networks and now our local area networks, both wireless. So, well, what are the, on this high level, things they have in common, and what are really differences? Think of, well, who's operating, administration, frequencies, etc. Just give some answers. So many things possible. Regulations, services, node capabilities. Well, the question is, the last question on slide 11, so what are the differences between mobile phone networks and wireless LANs on a high level? Yes, they technically they work a bit different, but you're right, there's no regulation of a big operator. So yes, the big mobile phone operators, they also operate wireless LAN networks, but there are millions of other operators, you at your home, for example. And so on these frequencies we do not need any license. This is why it's called license-free bands or license-exempt bands. So the coverage is completely different. You're right. So the cell diameters, 50, 60, 70 kilometers in GSM, LTE ranges to 100 kilometers, theoretically possible. And wireless LANs, well, you can be happy if you have the 100 meters you mentioned at home with some walls in between. To be realistic, 10, 15 meters. And after 15 meters, 2-3 walls, you already have some problems. Then the data rates are completely different. That because you're way closer to the base station, you can have much higher data rates. That's true. Compared to the classical systems like GSM. But if you compare LTE, what we learned about LTE and wireless LAN, looking at the data rates, the difference is not that big anymore. In the end, maybe there's no difference at all. Because, after all, they all have to obey the laws of physics. So there's no magic behind wireless LANs or LTE. So it's all physics. And as we will learn the newest standards of wireless LAN, they even come up with some LTE technology. So that's interesting. So they have also things in common. So they use channels, so frequency division multiplexing. So indeed, there's also this channelization of the spectrum. So we will see, we'll come back to the channels pretty soon. So you see, for these types of questions, you can come up with many different answers. So let's say these are typical questions you could also think of for exams, for example, because then you can write this and that and come up with interesting ideas, and we just check if the ideas make sense. So there's not the single best answer. Okay, that was basically an overview of the wireless LAN, and then I first looked into the physical layer, and here you will find exactly what you may know from home, these channels, these non-overlapping channels. And I also explained that yes, there are also some more channels, like the channel 2 and the channel 3 and channel 4 and channel 5 and channel 6, and no one forces you to use this or that channel. At 2.4 gigahertz you can do whatever you want. So we also looked a bit into the packet formats. Not that you have to learn anything about the packets, but what is interesting here, and this gives some hints towards the question why you, for example, even this old standard, why you will not achieve 11 megabit per second. Well, look what happens in the beginning, etc., etc. So, and then this, together with the medium access, well, I will come back to this in the context of one of the questions. But at least, so not learning the packets and the bits, but to understand that, okay, wireless LANs typically do not start with the extreme high data rate from the very beginning, but they start with a lower data rate because backward compatibility is quite important. You always have some older devices, and they will not understand if you start with a high speed immediately. So problems of carrier sensing, etc. Okay, so I explained a bit about this. I showed you also what's going on at 5 gigahertz, and then also a bit about the higher data rates, with ending at the physical layer with a system that's officially called the VHT, very high throughput system. It's marketed as Wi-Fi 5. I told you a bit about the Wi-Fi Alliance. They do this marketing, testing, compatibility check, and IEEE, they do the standards. And so this is the current official highest speed in the standard from 2016, but I will come back to higher speeds in the next session. So this is technology, the .11 AC, that was the old standard, integrated or substandard, integrated into the real standard, that already offers pretty high data rates. I mean, so this is quite a lot, 6 gigabit per second for the access points. So these are the access points we also use on our campus. Okay, again, important are not all these figures, just the capabilities. Now we use MIMO. MIMO, you know, MIMO technology, so several antennas for sending, receiving, and we can split the data stream, saying, okay, 4 antennas, for example, for digital TV, because we need 4 gigabit per second or 3 gigabit per second, or some antennas for a tablet and the single antennas for the smartphone, because that is enough. And what we also learned is that if you have only new devices, that was the idea here, if you have only new devices, then suddenly you can define complete new types of packets. But as soon as you have some kind of a mixed operation of legacy devices and new devices, those systems will fall back to some kind of a mixed behavior, so that the old devices still recognize there's something going on in the medium. Because as you know, the sensing of the carrier is extremely important for the wireless LAN. In contrast to mobile phone systems where you have a base station that tells you now you are allowed to send and this is your time slot, for example, or this is your code or frequency. Here in the classical scheme, we need the carrier sensing. I will come back to this in the next section. Okay, but first, the physical layer. So, physical layer, I told you something about the non-overlapping channels. Why is this non-overlapping that important? So we have 13 channels at 2.4 gigahertz in Europe, but only 3 non-overlapping. So why is non-overlapping important? Spectral overlap does not affect the performance of networks which use them. Are you sure? Does not affect the performance? So if you overlap, so you have your channel here and your neighbor is here, they should be non-overlapping. Why? The reason is simple. If your neighbor starts sending here and you perform carrier sensing on your channel, there's enough energy in your channel that your device will say, oh sorry, the channel is already occupied. So if you have, for example, channel 1 and channel 2. So the problem is, as soon as you have neighbors sending on, well, channels that overlap, especially if they send on the same channel, but if you have overlapping channels and your neighbor, for example, is using this channel, then the carrier sensing of your devices has a problem because it detects energy. And if it detects energy, it will say, okay, something is going on this channel. So as soon as you have this overlapping, then your network, well, will have a lower performance. So the data rate will simply go down because it's not only your devices using your channel 1, for example, competing for the medium, but it's also now the devices of your neighbor. And if you have non-overlapping channels, so 1 and 6, for example, they are non-overlapping, then your neighbor could use this and there's no interference. That's a big advantage. So if you can avoid the overlapping, that's fine. And this, by the way, is what your routers, wireless LAN routers, try to do. So they can automatically adjust the channel they use. The problem is today, more or less all the channels are used by too many neighbors. So if you can control the setting, for example, on a campus, that's what we did, then you can say, okay, our access points, they know they use only 1 and 6 and whatever 13, and then, or 1, 7, 13, 1, 6, 11, depending what you want to support, and then we have non-overlapping. And then you have to check in 3D space that you have no overlapping with other different floors, etc. But this is something you could do. So the problem indeed is that as soon as you have wireless LANs, let's say your neighbor watching TV over a wireless LAN on an overlapping channel, your data rate will really drop dramatically. So sure, if the neighbor is not active, or if the neighbor switches to another channel, problem solved. That is what many people experience right now doing many of the video conferences, that they say, well, I have a wireless LAN and this has hundreds of megabits per second. Yes, but especially in the evening when many people use their whatever TV sticks watching TV over wireless LANs, then the performance will break down. The point is, inside your own wireless LAN network, your wireless LAN router, with the help of the standards, so there are parts of the standards, can optimize the use of audio, video, whatever, voice over wireless LAN, telephones. But as soon as the neighboring wireless LANs are overlapping, well, what can you do? It's an unlicensed band, so everyone can send. And as we will learn, also Bluetooth is jumping through these channels, and also Bluetooth may interfere with the wireless LANs. So there are also some standards that try to avoid this jumping into your channels. So the problem is, as soon as you have a dozen or 20 or more wireless LANs in your neighborhood, all the channels are occupied. One solution is, was in earlier days, that you switch over to 5 gigahertz, because at 5 gigahertz you have many more channels, non-overlapping channels available. So that was one of the solutions, but nowadays also on 5 gigahertz you have many more users. And in addition, just to tell you why 5 gigahertz is not always the solution, the point is that here this is 5 gigahertz, many more overlapping channels, but to achieve higher data rates, the systems do not only use one channel, but sometimes combine 2 channels, or sometimes combine even 4 of the channels. So they try to use more or less a larger part of the spectrum. So do have a look, just go into your wireless LAN router, check the frequencies used, and you will find, okay, they need more than, let's say, the roughly 20 megahertz. So they allocate several channels. And if now more and more neighbors do this, then you have more and more overlapping also at 5 gigahertz. So yes, you may try to avoid this overlapping, but it's unlicensed, so that's a problem. So hopefully you can get non-overlapping channels, but there's no guarantee. And without any neighbors, 1.6.11 or 1.7.13, these are the non-overlapping channels. And 1 and 2, yes, they overlap. Okay, so besides this overlapping, the next question is, why is the user throughput much lower than the available data rate, the maximum available data rate at the physical layer? So we have something like 54 megabit per second offered, but all you see is 30 megabit per second. Why? What are the reasons? You share the medium, that is one reason, that is the collisions with other or the problem of carrier sensing. So you cannot transmit continuously. That's right, that's one of the reasons. Now let's assume you have the medium, it's completely free. So no one else is on the medium. Still, you will not reach the maximum data rate. You have large overheads. Exactly. So the point is, even without this, well, problems of with the neighbors, you have this headers, and you see in this example operating at 1 megabit per second, independent of the data rate you have later on. The same is true on higher data rates. Also here you have some additional overhead. Again, you don't have to know this overhead. It's just to show you there is a lot going on, training fields to get synchronization, etc., and service, etc. stuff. And then in the end, a small part here inside, this is the user data. There's padding and tail bits and this and that. But you see, there's a lot of overhead. And the next point is, well, this is only the physical layer. If we look a bit ahead, then you already learned in the next section that we have a lot of interframe spaces. That means time where I do not send anything. So wireless LANs have to wait before they access the medium. I will come back to this in a second, but that's a layer 2 issue that contributes to the lower data rate. So on layer 1, we saw, okay, we have the overhead, we have packet headers. The packet headers are usually transmitted with a lower data rate. And on layer 2, additionally, you have the waiting time, even without a neighbor. You have waiting times. We'll come back to this. Before you can send your data. So that means all this together, waiting on layer 2 and sending on lower data rate layer 1, this all contributes to the overall lower data rate. Because this maximum announced data rate, this is only achieved inside the data packet at full rate if there's no interference, no neighbor, nothing. And this is one of the problems in general with wireless LANs. So yes, they may announce high data rates, but you cannot really achieve them due to the medium access scheme, your neighbors, and the overhead and the physical layer. So there are several reasons. So I already discussed a bit about, well, going to higher frequencies. The advantage was we have more non-overlapping channels. What are disadvantages? 5 gigahertz, that's fine. The newest wireless LANs, they go up to 6 gigahertz. These are the new standards. The Wi-Fi 6E, they go up to 6 gigahertz. So what are disadvantages? Range, yes. Just test this on your own. You will see that depending on the distance in your apartment to your wireless LAN or wherever you are, you will see 5 gigahertz devices maybe in the next room, yes, but if you have 2 or 3 walls in between, 5 gigahertz is not an option. It simply doesn't work any longer. So then the 2.4 gigahertz may still work, but 5 gigahertz, that really is a problem. So the data rate simply drops because in the end, the high frequencies means a lot more attenuation. So that was again here in our 5 gigahertz example. There's just rough numbers. Okay, 54 megabit per second up to 5 meters, but only 12 up to 60 meters. Now, even without a wall in between. So that's indeed the problem of the higher frequencies. You have really attenuation, a lot of attenuation in the walls, everything. So lower frequencies penetrate walls much, much better. We learned this already. So remember firefighters, police trying to use 450 megahertz and not the higher frequencies. So physics, well, that's physics. That's the nature. It's true for wireless LANs as well as for other systems. So that's our problem here. Okay, and then at the end, we saw with the different physical layers, we can achieve now pretty high data rates. So what contributes now to the higher data rates? Yes, we have new technology, but what do the systems do now to achieve these multiple gigabits per second? You could try to have different channels for different networks, but as we saw, your neighbors will not ask you. MIMO. So MIMO is one of the things, yes. So if you mean by a separate channel, if you mean this beam forming and splitting the data streams over different antennas, yes, then you have these separate data streams as we saw in this very high throughput standard. Then exactly we go for higher modulation schemes. So modulation contributes a lot. So if we use these higher modulation schemes, that's just an example here. Please don't learn any of these numbers, but you see we use many more points in the constellation diagram than to reach this, whatever, 6 gigahertz, something 6.9, almost 7 gigahertz. So the modulation changes a lot. So that's quite important. Then you wrote distance to other network on this same channel. That's true. So if you stay away, if you can, or your network can stay away from interference, that also contributes. So you try to avoid interference if possible. So the wireless LAN routers, they detect interference on the channels and try to dynamically select another channel. And then they also do something, they simply use more bandwidth. So what they do is they, as I showed you, they do not only use a single channel, but 2 or 4 channels. So not only 20 megahertz, but maybe 40 megahertz or 80 or 160 megahertz. The problem is, again, overlapping, but the advantage is if you do this only for a very short time, then the probability of interference with your neighbors is lower. So you can transmit for just some milliseconds or second or whatever you need at very high data rates using a larger part of the spectrum, 160 megahertz instead of 20 megahertz. And this is one way of achieving higher data rates. Sustained data rates, so that you can really have the data rates for a longer time, that is difficult. So your wireless LAN will not offer you a sustained data rate of all the time 6 gigabits per second or something like this. That's a big difference to wires. If the wire gives you 100 megabit per second, which is much lower, well, you will always have 100 megabit per second. So that's the point. So you have some more questions related to this. Yeah, is it a good idea to share with a neighbor an access point? Yes, it can be a good idea if you have a really powerful access point and you together use only one access point. Then this access point knows how to handle the different devices and how to avoid interference. If you have 2 access points, then you might create interference between the access points because they do not really coordinate each other if they do not have the newest versions of the standard, because when I come to 11AX, you will see there is some coordination included. But the normal wireless LAN of today, there's no coordination. So then it could indeed be a good idea if your neighbor especially has a better internet connectivity, then it's a good idea to have fewer access points that are more powerful compared to access points that interfere with each other. Next question, do repeaters influence each other? It depends. So there are different types of repeaters. So repeaters, what is the idea? You have your access point here with the antenna, and then you have your signal, and the signal gets weaker and weaker. And one idea is to have then a repeater that actually, let's draw it this way, your repeater that receives the data and then sends out again stronger signal, and maybe you're here with your tablet. So why do I say it depends? there are different types of repeaters. So first of all, but we'll not look at these, there are repeaters that have a wired connection to the access point. So this is some kind of cheating. Well, so then there's no big problem of interference. Then the repeater simply takes another channel compared to the access point, and then there's no interference. But even with repeaters that have, let's say, that receive over the air and send over the air, there are two different versions. There's one version that's the cheap one. The cheap version simply receives something and then sends on the same channel. That means the repeater is competing for the medium, well, for the same channel as the access point uses. That's one way of doing it. And then it's for the device will stay on the same channel, and you actually only repeat the signal on the same channel. But you can also have a version that uses two channels. So if you use the channel 6, for example, here from the access point, and then you go here on the channel 13, this means you can send at the same time or as the access point, and there's no collision. The problem is if the repeater uses the same frequency, that means the same channel, then the repeater is just a source of interference for the access point or for the medium on this channel. So there are repeaters that use the two channels, and then you can operate and also receive, for example, something on this channel 13. So it goes in both directions. So the device uses one channel, channel 13, and the repeater then uses another channel with the access point. That is a better idea. So you also ask if you have a reverse signal near the repeater. Well, it depends on which channel you are. In our example, if you are on channel 13, then the repeater has a strong signal on this channel 13 and trying to send this out, this data. And then you have a strong signal. But your access point signal is relatively weak. This is why you have the repeater. But it has to be still strong enough so that the repeater can receive the signal. So you cannot place the repeater in the same problematic location as you have maybe your tablet where you have no reception. So the repeater should be, well, roughly somewhere in the middle between the access point and your tablet or mobile phone or whatever. So if you look at repeaters, take care that they really can operate at the same time on two different channels. Or even better is if you use a cable, if possible. Cable is always better compared to wireless transmission when it comes to really low delay and no interference. It's not about the data rate. The data rate is pretty high over the air, but interference, that's always a problem. Okay, so repeaters, well, they help, but they also may contribute to interference, especially if then you're close to the channels of your neighbor again. It's just, well, similar problems you may have with the access point. Okay, so you see, higher data rates, there are different ways of achieving this, MIMO modulation, interference, using simply more bandwidth. So, okay, with all the problems. Next question, quality of service. Can quality of service make my connection slower? Quality of service basically in a second, in the next section. Quality of service, that's something the basic wireless LAN cannot offer, but as soon as all the devices know how to handle quality of service, then they can use this. Quality of service, that means that you have certain, well, guarantees, maybe not, but the system tries to give you some guarantees when it comes to delays, data rates, these things. So quality of service, that's something you know from classical telephone networks and something you do not know from the classical internet. Classical internet has no quality of service. This is why we call it best effort. So the IP packets, this is best effort transmission, and telephone, classical telephone, has certain qualities of service, guaranteed data rate, for example. Now coming back to your question, so indeed, if you use quality of service, that means you prioritize voice over IP devices, audio video, then this could slow down the other devices, because then they cannot that easily interfere with your device. I'm not talking about the neighbors. Neighbors can always interfere, but if you actually use certain quality of service settings, then this could slow down other devices, because there's a trade-off. I mean, you want to guarantee something. That means you need some guarantee access. Well, guarantee. It's not 100% guarantee, but the system tries its best. So you need some time for the access for then the phone or the tablet or the TV. And this leaves less time for accessing the network for other devices, or devices with lower quality of service. And indeed, I will come back to this in a second. This could then slow down the other devices. And this has something to do, that exactly fits to the next slides, with the medium access. I showed you that the classical medium access scheme, which I also explain in more detail, and that's the foundation for everything, it's called a distributed coordination function. This is the basis for all the other access schemes. Distributed, that means there is no boss in the network. Not even the access point. So all devices are equal and they all have to compete for medium access. So that's the core in the standard. And you see here we have our physical layer. That's this very high throughput. There are special versions, TV, etc. Not that important here. So VHT, that's in the standard. And so we covered this now, and now the DCF, that's the heart of the medium access. And on top of that, we can have different additional optional functions. For example, this hybrid coordination function with contention access, also called EDCA. That is something needed for quality of service support. There is still contention. That means the stations, they have to fight for medium access, but we can support quality of service. And now coming back to your question, the point is, and that was on the next slide, exactly this enhanced distributed channel access. This offers you different priorities. And this is called wireless multimedia in the terminology of the Wi-Fi Alliance. Wi-Fi wireless multimedia designations. And now you see that if you have, for example, video and voice, they will win over, for example, background and best effort. Best effort, that's file transfer, for example. So your TV set will get a higher priority for medium access compared to, for example, your normal, let's say, whatever system. And so the point is, it's not that you reboot your system and then everything is faster or whatever, but it's a question of setting the priorities. And this is what your base station, the wireless LAN router, does. So if you look up in the router, you will see that the router sees some prioritized traffic, standard traffic, background traffic, whatever. And these are the different traffic classes. So there is some quality of service support built in all the newer devices called wireless multimedia. Because the problem is, indeed, if you have multimedia devices and you operate them over wireless LAN, there might be some problems. Again, as soon as your neighbors also send, well, you have interference, you have collisions, you cannot do much about this. It's an unlicensed band. So if I say guaranteed quality of service, it's not a guarantee in terms of mobile phone networks, where you have a single operator and the operator then guarantees you something. Here it's rather you try to prioritize the traffic. And how this is done, this is exactly where we are now in our, well, the heart of the prioritization. You have certain different waiting times for these priorities. Depending on your quality of service class, if you're audio, you're very sensitive to delays, or if you're background, well, you don't care, you will get different waiting times. So for example, audio will get a shorter waiting time compared to, let's say, background. By assigning different waiting times to the devices, you also give them the chance to access the medium earlier, before another device can access the medium. Because, as you learned, medium access is controlled by carrier sensing and waiting times. As soon as you hear that there's some communication going on, you will stop trying to access the medium. Because if you access the medium at the same time, we'll have a collision. So, the basic idea is now you give the devices with higher priorities a shorter waiting time, and then they will be first, they will be the winners accessing the medium. Still, there is competition, because even here you may have several devices and then it sooner or later it doesn't work. So there's no magic behind. It's just one way of trying this. Plus, if there are some other devices, they do not follow this. They simply, well, start sending earlier, or there's other type of traffic, then your audio device can also not win. You see, this is all on top of the classical access scheme. The classical access scheme, there you have the short interframe space and the DCF interframe space. So the classical access scheme does not know anything about these priorities. So only if all the devices know this and they behave accordingly to this part of the standard, it's all part of the standard, but not all devices use this. But so if they are compliant to this wireless multimedia, then they use these different priorities that are reflected in different waiting times, and then you can implement different service classes. For the normal old classical devices, nope. And the old classical devices, they operate always with this. This is the basic scheme, as I explained. This waiting for a certain time, then getting a random number, waiting for a time according to the random number. If the medium is still free, accessing the medium. That was the basic idea. If two stations have the same random number, or if the remaining time and the random number is the same, well, they access the medium at the same time, you run into a collision. And if we all put this together, this was one of the most important slides here. If you understand this, you understood the basic access scheme. So this is where you can see what happens here. Medium is free. You always have to wait for a certain time, and then you will get your random number, and there are the losers getting a large random number, and then maybe there's the lucky winner with a very short random number. It's all random, and there's someone in between here. Depending on the random number, they wait random number times slots, waiting slots, for example 20 microseconds, and then you access the medium. If during this waiting time the medium gets busy, you will stop counting down. You're not allowed to access the medium. You will simply stop counting down. Though that's the point. That happens exactly here. At this point, station 2 accesses the medium, and 5 and 1 stop counting down. This leaves a residual back-off time. So now the next time they do not have to draw a new random number. They will simply reuse the remaining time. That's all they do, reusing the time. And the whole game starts again. They start counting down. And if the countdown is at 0, the medium is still free, they access the medium. The problem here was, that now we also have a station 4 with a new random number counting down, and well, it's a random number. So they both, 4 and 5, access the medium at the same time, and we have a collision. This may happen. Okay. So if there's a collision, the next time they both have to get a new random number. And station 1, yoo-hoo, finally has the lowest value left, the lowest back-off time. And then now station number 1 may access the medium. So the point is, station 4 and 5, they send at the same time. Station 4, because I picked a low random number, lucky winner. Station 5, okay, it may happen that the residual back-off time is exactly the same. There could be 100 more stations with having the same number. But if they send at the same time, because the medium was free, then they can access the medium, a collision occurs. They're not coordinated. So the medium is busy for station 4, it sends, and also for station 5, the medium is then busy because you send. What you cannot do is listening to the medium while you are sending. That's not possible in the wireless systems. That was done in the classical Ethernet, but not here in wireless systems. So you send your whole packet, and you will not notice that there's a collision. The first time they notice that there's a collision is station 4 will not get an acknowledgement and station 5 will not get an acknowledgement. So no acknowledgements by the receivers. That's the point. So if there's a collision, no one notices until, you will not receive an acknowledgement. And the point is, you expect the acknowledgement immediately. That was exactly the thing I showed on the next slide. So if you send your data, immediately you will get an acknowledgement. So all unicast packets are acknowledged on layer 2. If there's no acknowledgement, you think, okay, either the receiver is dead, or more likely there was a collision. And then you can repeat sending. So there's always an acknowledgement. So that's the point. So all these collisions or no collisions, they're all controlled by this random picking of waiting times. So you cannot actually be a perfect member in the wireless LAN trying to avoid everything. No. So in the beginning, you will simply pick a random number, random waiting time out of an interval 0 to 7. So that's just random. So all waiting stations, after waiting for the stiffs, they pick a random number. And as soon, this is for the so-called initial attempt, as soon as you have a collision the first time, you will simply double this collision window, 0 to 15, etc. You double again, you double again, you double again until you reach this 0 to 255. What does it mean? You double the interval used for picking the random numbers. and this spreads out the random access of the devices under heavy load. Because if you have heavy load, you will have more collisions. If you have a collision, you double the collision window. That is the idea. So the question is, can a non-standard compliant station just permanently pick a low random number and then you have a higher data rate? Yes, absolutely. So if you disable the mechanism and you pick always a 0, that means you do not wait. Or even worse, you simply send immediately after the medium is idle again. This is let's say the worst thing you could do is, okay, medium is busy and you start exactly here. That's your evil station. Then yes, you are automatically a winner, always. And this is basically, if you tweak your firmware this way, you're not standard compliant anymore. And then your station is the winner. Can anyone say, oh, this is illegal? Well, it's a license-free band, and we also have something like Bluetooth. Bluetooth does not wait until the carrier is free. No, it jumps all the time right into your channels. And it's fully legal. So the point is, you're not well behaving, but to be honest, if this is legal or not, I don't know. I mean, it's license free, so you can do. You're not allowed to have too high transmission power, so this is regulated, maximum output power, these things. But being evil in this sense, okay, not nice. But tweaking the firmware, okay, could be that tweaking the firmware violates some checks because it's a radio modem and you have to check this to say, okay, this is compliant to whatever. But in the end, well, you can do many things. Use a software-defined radio and just send immediately right after the medium is idle again. So indeed, yes. So if you pick a low random number all the time, okay. Not nice, but feasible. So the idea is that by picking random numbers, you see if you have competing stations here in a larger interval, you will spread out the random numbers. Well, you could pick the same random number, but the chances are lower compared to this small interval. So each time you have a collision, you double this window, the collision window, up to a maximum, and then you stay with the maximum, and then you have a maximum number of retransmission, attempts. So that basically is the idea here. Okay, so you see, this really is different from the medium access you have in a mobile phone network, where you have your eNode B, Node B, BTS controlling what's going on. And the only random thing in your mobile phone network is the random access channel. So there are certain time slots where you may compete for the medium. That's different here. So the random access channel, this is where you may have collision mobile phone systems. Again, sure, if you manipulate your broadband modem, then you can also send whenever you want, but here the base station, I guess, will not really accept it. So that's the point. Okay, the question you come up with, the longer you use the Wi-Fi without reconnecting, a higher possibility is to have a higher number after collision. Okay, that exactly leads us to one of the questions. I will come back then to your question. We will jump exactly to this. Why is the contention window mechanism unfair? I guess this is what you mean. So the point is, after each collision for a certain packet, not forever, but for a certain packet, the collision window doubles. So now, think of this mechanism. Several stations want to send. This mechanism is used to spread the random numbers in larger intervals. Why is this mechanism unfair? This is something to do with your question. Why is this unfair? You will get a higher window each time you experience a collision. Everyone does this, but exactly, new clients come in. If you are new, let's say the many old waiting here, and this window is already 0 to 255. The new one comes in and says, "Yoo-hoo, I'm new." The new one starts with a lower, a much smaller interval. It's not coordinated. So there's no access point distributing intervals to the stations. It's a distributed system. So each time a station experiences a collision for a certain packet, it will double the collision window. And if there's a newcomer, oh, I never experienced a collision, great. I pick a small interval, and this will lead to way smaller numbers. So somewhere between 0 and 7, maybe a 5. And here the chances are much higher that you pick a 200. So the older stations are the losers. You do not have to reconnect. No. Picking a larger and larger interval is valid only for a single packet where you experience collision. So you want to send your packet 1, and then you have a collision, and then you have success. So that means here you start with 0 to 7, then with 0 to 15. After you're successful, the collision window goes back to 0 to 7 for the next packet. So after being successful, the window is back. So then everything is fine. So it's not for all the time. Well, there might be different implementations, but it's not the case that you, in the end, have always, if you're a station that is longer on the network, that you are always a loser. No. As soon as you're successful, you're back in the game with the smaller intervals. So do not restart your networks or whatever. It's just that if there are already stations waiting for a longer time in a congested network, newcomers, well, they will have a smaller window. That's the point. So the next question is possibility out of order packages. Well, the point is you as layer 2 try to transmit a packet. And as long as you're not successful, you're trying to transmit this packet. So there's no other packet that can be faster or something like this in the classical normal standard case. I'm not sure if you there are not implementations that say, okay, or most likely there are implementations that say, okay, I have different queues for different priorities, and they will have different probabilities. And then indeed, if you have packets of different priorities, you will go out of order, but they belong to different data streams anyway. So it would not really make sense to reorder or the packets in the same priorities or for the same data stream. But hey, even if this happens, so what? Layer 3 does not guarantee anything at all. So you have your layer 3 that is does not order something, the IP layer. So why bothering at layer 2? So simple answer. But to be honest, I don't know, depending on the implementation, if the different data streams, then you may have packets that simply are on the faster lane. So if you have higher priority, then I'm pretty sure that you can overtake other packets. So they will be then out of order, but okay, that happens. So when you pick 0 as a random number permanently, the others are even lowering my chance for a packet collision. Yes, the others will always experience, well, they will not experience collisions, they will experience longer waiting times, because the other stations will see as soon as their turn, oh damn, I counted down 0, nothing. So the residual backoff time is basically the same, and the medium was already busy, so maybe they count down 1, the medium was busy, then I have to wait until next time it's my turn. Oh damn, again not my turn. Oh damn, again not my turn. So this would be a denial of service attack, I'd say. So this is denial of service, yeah, because there's no collision. Collision, that means you successfully accessed the medium, but there was no acknowledgement. Then the stations assume a collision. But what you propose is the stations will never be able to access the medium. That's even meaner. So that really is mean. So all the others, they have to wait. I bet there are also timers telling the stations, oh, okay, you waited for too long. Maybe change the frequency, or, well, tough luck. It doesn't work at all. But yes, yeah, never tried this. So you are asking for booster programs. There are different ways of boosting the performance. So indeed, one way of boosting is you ignore legacy. That's the simplest way, so that you can even switch this on in your wireless LAN router. You tell the router, I don't have any of the legacy devices. And then the router will use packets where legacy devices will not be able to identify them any longer. So the legacy devices cannot participate. .11b devices, for example, cannot participate any longer in the network, and this boosts the performance. Everything I explained so far with the medium access is, well, maybe not illegal, but boosting in a way that's not nice. So yes, can be done. I remember also TCP booster programs. I'd say, okay, you will always be the winner on layer 4 with TCP. We simply ignore congestion avoidance mechanisms. Yes, then you're always a winner. I mean, yeah, that's like driving on the right lane on the highway where usually only the police, etc. drives, then yes, not following the law can make you faster. But here we try to set up a system where we kind of balance out the different interests of the different stations. And then, yes, if you're abusing this, difficult to avoid this. It's different in mobile phone systems where the base stations can detect something. Also maybe on campus networks where our access points can detect something. So it's different. You asked for legacy devices. Legacy devices are old devices following the initial standards. So for example, if you have devices following 11b standards, then they cannot be as fast as today's devices. But, and that's even worse, they also slow down the whole network. If you have only new devices, the packet formats are different, and then you can only use, for example, high throughput packets. So that was something I showed on this slide, the so-called, it's called greenfield. So if there's no one else around for old versions, you don't have to use this old non-high throughput or high throughput mixed formats, etc. You can directly go to packets with less overhead. So that is the point. So you use less overhead and you can be faster in the end. So the problem is not your access point recognizing the device, adjusting the speed. The problem is your old device capable of detecting the new packet formats in a way that it detects energy on the channel? So it could be, and that's the worst case, that your old device will not be able to detect that the medium is busy, because it simply says, oh yeah, there's some little noise going on, not knowing that this is the new packet format. And then the old device will simply access the medium. And then we have a problem. So the old device will slow down your network. Now that's the point. But today all the new devices, so you don't have to care for this if you have new devices. Okay, some more questions left here. So to start with the first one, guaranteeing quality of service. So you see, your questions are way more complicated than what I expect from you. So coming back to the simple questions, guaranteeing quality of service, and that's the big difference to cables. As you noted, oh, maybe cabling is a good idea. Yes, sometimes it is. So there are quality of service support mechanisms, but guarantees, what is the problem? Guaranteed distributed system, guaranteeing, well, yes, this has something to do with the distributed mechanisms, because as you saw, it's kind of, can be unfair, the mechanisms. They simply can be unfair. Then, in addition, the MAC layer cannot control interference by neighbors. You may have problems hidden exposed terminals. You may have problems other stations having the same quality of service. You have a randomized access scheme. So what can you do with a randomized scheme? It's difficult to guarantee something. That's quite similar to the mobile phone network, where you cannot guarantee the initial access to the phone network, but then you can give some guarantees. But the initial access you cannot guarantee. Prioritization. Talked a bit about this. You should know this. How do we prioritize different types of packets? That's always the same. Prioritization is mapped to. How do we do the prioritization? Prioritization via which mechanism? So we have acknowledgements, more important. Waiting time, yeah, waiting time, exactly, that's all. It's just like, well, prioritization when you bought an aircraft. First business, economy class. It's all the same aircraft, but waiting time is different. Okay, so the waiting time, especially also randomization, can be, well, the waiting time, the windows, they are different for different packet classes, but it's randomized. Quite important is, now it seems like wireless LANs, oh, so many disadvantages, but they also have very nice advantages, and this has something to do with the behavior of the access method under no or light load compared to heavy load. But what happens under no load, light load? So why is this scheme, well, quite nice compared with mobile phone system or whatever, or other access methods? Especially if we have no load. So if you have no load, you have, well, to wait a bit, but you can always, yeah, the waiting time does not change. You can almost immediately access the medium compared to a mobile phone system where you first have to ask, am I allowed to access the medium? And then you will get some frequencies, some resources. You have extremely low latency under low load. And that's exactly the point. Low latency under low load. So that means at home, if there are no neighbors, you're living on the countryside, that's fine, your wireless LAN. Very low latency, immediate access, fine. What happens under heavy load compared to a mobile phone system? Now talking about the user data. More collisions, waiting time is rising up to complete breakdown of the system. So the point is, if you have really high load, many neighbors, evening, a lot of data transmission, the system can break down, simply, because you have only collisions and that's it. Maybe you've experienced this already watching video, etc. in the evening, then suddenly everything stops and then it takes some time and then everything is reconnected, etc. So that is really a problem. I talked about the unfairness of the potential unfairness of the contention window mechanism, but there's also a certain fairness implemented in the mechanism. So in what respect is the mechanism fair? Think of several stations, one to access, only one is a winner. What happens to the loser? Why is the system fair when it comes to the loser? What can losers of the contention do? Contention is not collision. Reconnecting, that's too hard. No. Look here. We have here several losers. We have one winner, station 2. And the point is, the next time the losers of this first round want to access, they do not have to pick a new random number, but they use the residual backoff time. Exactly what you say. The waiting time gets shorter every time. So it's a decreasing value all the time of the residual backoff time. So statistically, the chances of being the winner, they increase. So the longer the way you wait, so the higher is your chance to access the medium. So that's the idea. The unfairness I was talking about, this is about collisions. Now we are in the phase of competing for medium access. This is not a collision. This is just who will be the winner? And you see station 2 is our winner, 1 and 5 are the losers. But the next time, the losers reuse the remaining time. And as you see, station 5, now no new random value, but using the residual backoff time. So what remains of the backoff time? And so this is why sooner or later you will have a pretty low waiting time. This means you are the winner. You have to pick a new random value after a collision, but that's different. So that's a collision. But here shown in red, that's always this contention phase. So where contention, where the stations try to be the first to access the medium, but there's no collision. It's just they're just silent and they wait for their time. So they do not access the medium. So that's the difference. So it's fair in terms of if you wait for a longer time, your chances increase to access the medium. Okay, unfairness, we covered this already. And then we had something special, so-called network allocation vector. What was the idea of this network allocation vector? Does anyone know? Shown here in green. Network allocation vectors are stored internally in the stations. And the basic idea here is that as soon as you hear a packet, the packet contains, let's say, a duration. How long does it take to send the packet? Then you also know, okay, there will be an acknowledgement. This means, for example, after receiving a certain packet, a station knows it has to be silent for a certain time. So you could even power off your transmitter, save some energy. Because now you know, okay, there's one station doing the communication for a certain time, some milliseconds. The medium will not be idle again before everything has been done. That is the idea. So you can wait for a certain time, so you don't have to send. So don't try to access the medium for this time. So this basically gives you an idea of how long the medium will be busy. This can be updated over time, and only after this network allocation vector indicated time ends, then you wait, and then you start with the normal contention, etc., and continue. So the idea here is that a network allocation vector tells you how long the medium is occupied. That means you don't have to check all the time. You don't have to check, oh, is the medium still occupied? Is it still occupied? Is it still occupied? So nope. Well, forget it. You wait for this time, and then you can access the medium. Yes, if you want to attack, just send around a really long network allocation vector. Then everyone is silent. Also a good idea for denial of service attack. Okay, that is the idea of the network allocation vector. And I will come back to this. I mentioned this. The reason is that if you receive something from your neighbors, this also sets your network allocation vector. Because your station doesn't know if this is your network or the neighbor's network. And so it can happen that your neighbors also basically make the network allocation vector longer, and you will not send. This is why the newer stations, they have different network allocation vectors, one for your network and one for the other networks. So yes, but as soon as you have a mechanism built in, you can abuse it and whatever. So this is just, if you hear this term network allocation vector, this is what it's used for. And the last question, well, that's already the right slide. Hidden exposed terminals. How is this problem solved? And maybe you saw this in your network adapter somewhere, this setting. You see it here on the slide, how this is solved already. RTS, CTS. These are exactly our two packets. And the only case where you may have collisions are here, the CTS packet. Here something can happen. After that, you only have short interframe spaces the whole time, so nothing can happen here. Unless you have interference or mean, evil, whatever stations. But if you all follow the standard, after successful transmission of an RTS, nothing can happen. Because then we use only the short interframe spaces, and then we send all this and everything is nice. If you do not know what was this, please do have a look at hidden exposed terminal problem. I explained this in one of the earlier chapters. So, and this is just an example that you can also fragment packets. Fragmentation, that means you can split up a longer packet into shorter fragments. So that is the idea. Why doing fragmentation is quite simple. The probability that bit errors destroy a fragment increases if you have longer fragments. Because if you kill single bits, this kills the packets. So that means if you have smaller fragments, the probability is higher that you will not have a bit error in the fragment. And if you have a bit error, you can retransmit this part. So fragmentation can also be used for too long packets. That's the idea here. Okay, so hidden exposed terminals, that's also included. Just to have a look at your own network drivers, adapters, whatever you have, and then maybe there's a setting called enable this in case of high interference, something like this. Then this is RTS CTS, but RTS CTS will decrease your data rate. So this is not always a good idea using RTS CTS. There's sometimes even strange behavior if you use RTS CTS and voice transmission, etc. So that all things have pros and cons. Okay, so you see, although the standard has only 3,500 pages, there's a lot in the standard. But as you also saw, no one expects you to know all the details. This is just to give you some background. Why do we have now these high data rates, and how is this working, etc. So the next time I will cover the latest version, just to give you an overview of what is .11ax, that's Wi-Fi 6 or even Wi-Fi 6E, the newest products now on the market. And we'll wrap this up with wireless LAN, and I will introduce the classical Bluetooth basic rate, enhanced data rate, how Bluetooth works, because this is really different, and then give also a brief overview of Bluetooth low energy. What is the difference here? Because this is really a different system. And a bit about Zigbee, and that should be all on these local area networks before we then go to higher layers, the internet, mobility support, etc. So, are there more questions related to wireless LANs? Okay, thanks a lot. Bye.